In this video, we're going to go over the mechanics of matrix population models, get a little more familiar with how to use them and what a transition matrix really represents and what it means. So what I'd like to do is to first start with this stage structured population model in InsightMaker. This is the same model that we have that we looked at in the age-structured population lecture. And let's just clone it and open it. So, oops. Open this model up here. And so here's the model, and what we're going to do is take something we know, which is an InsightMaker age-structured model, where you have, in this case, a relatively simple structure. We have 3 stalks, and each stalk is associated with a mortality flow and a transition to the next stalk. And let's see, the adult stage is the only stage that contributes new offspring into this birth flow. And so this is a model that we hopefully understand at this point. And what I'd like to show you is that this model is a matrix population model, essentially. We basically just have to take the numbers that we put in these variables, these vital rates, transition rates, mortality rates, fertility or birth rates, and translate them into a matrix. And what I'd like to show you is that this model, which looks like this, and you know, we can see how the abundance changes over time in each of these stages, that we can replicate this model exactly using a matrix population modeling approach. So we're going to take something we know, InsightMaker, age-structured InsightMaker model, and we're going to translate it into a matrix population model, and we'll write the matrix population model in R and do some population simulation. And we can demonstrate, hopefully, in this video, that these 2 ways of representing the population are equivalent. All right, so we're going to take this model and translate this into a transition matrix. So let's go into the whiteboard. And first of all, just recognize that we have 3 different stages here: juveniles, subadults, and adults. And when we start putting together a matrix, there's going to be 3 stages on the 3 rows to this matrix and 3 columns, each row and column representing a stage in the life history of this species. So let's look at that. So we're going to have 3 columns and 3 rows. And we can name each of these exactly the same name as we gave these. So we have juvenile, subadult, and adult. That's going to be the names of our rows and our columns. All right. So juvenile, I'll just say J, subadult, and adult. Juvenile, subadult, and adult. Now, in a transition matrix, we can interpret each element, that's each box of this transition matrix, which is each going to have a number in it. Each of those numbers represents the transition between whatever the column name is to whatever the row name is. So, like this element here would be the transition between subadults in this year becoming or producing juveniles in the next year. So you can almost think of that as a reproductive transition. So in order for a subadult this year to be able to produce a juvenile next year, they basically have to give birth in this year so that they produce a juvenile. Now, if we look at this element here, this is the transition of a subadult this year into an adult next year. That's basically a growth. That's just a subadult becoming an adult, right? So we can think of this number as basically the probability of a subadult that's alive this year to survive and become an adult next year. What about this center element? That would represent the probability of a subadult this year surviving and remaining subadult, right? That is not, it survives, but it doesn't transition into adulthood. All right, so let's look at, what we're gonna do now is just try to fill in these 9 elements. And let's look at the InsightMaker model and start filling in these elements. First of all, let's look at this flow here. That is the flow of juveniles becoming subadults, surviving and becoming subadults. Now, we see that there's a 0.3 transition rate or probability of transitioning from juvenile to subadult. And we see that the juvenile mortality rate is 0.7, right? So we have 0.3 and 0.7, that is everyone, all the juveniles either die or they transition, right? Because 0.3 plus 0.7 is 1, so there is no other option. Juveniles can't really stay juveniles. They either have to move on and become subadults or they die. So that is how this population works. And let's look at how, like, which element of this matrix can we put that 0.3 in. 0.3 is the probability of a juvenile this year transitioning and surviving and becoming a subadult. So we can just write that in right here. So that is the first element that we'll fill in this matrix. Let's go back and look at this flow here. That is the probability of surviving of a subadult this year, surviving and becoming an adult next year. The transition rate there is 0.1. Going back to the matrix, we see that the probability of transitioning or of a subadult this year transitioning to become an adult next year is 0.1. All right, let's go back and let's look at the subadult mortality rate. We have subadult mortality rate is 50%, so it's the probability of a subadult this year dying within the next year is 50%. Again, the transition rate is 0.1 here from subadult to adult. So we have mortality rate of 0.5, transition rate of 0.1. So there is actually 0.5 plus 0.1 is 0.6. So there's still 0.4 left to be accounted for because, subadults, something has to happen to subadults. And so the probability of that, of dying is 50%, 10% chance of becoming adult. So you still have a 40% chance of remaining subadult, right? Because if you don't die and you don't transition, you just stay subadult. And that's the first, a little tricky part of translating this model into a matrix. But let's go ahead and do that. So we will get back here and change this to 0.4, right? So that way we have a 40% chance of a subadult surviving and staying subadult, and a 10% chance of a subadult surviving and becoming an adult, and that leaves a 50% chance of dying, right? So your total survival of subadults this year is 0.4 plus 0.1, and so the total chance of surviving is 0.5, and therefore the total chance of dying is also 0.5. All right. Let's go to adults. So if we move on to adults, we see that you can't transition beyond, you can't grow beyond the adult stage. So the only thing adults can do is either they die or survive. So this one should be relatively easy. There's a 15% chance of dying, which translates obviously to an 85% chance of surviving. All right. And so that's a pretty easy one. We can just go fill that in. 0.85 is the chance of surviving. I'm an adult this year, surviving to the next year and staying in the adult stage Otherwise, you have a 15% chance of dying. All right. There's a couple other easy ones we can fill in, like the probability of a juvenile transitioning to an adult. We don't see that flow. That flow doesn't occur from juvenile to adult, so there's a 0% chance of a juvenile this year becoming an adult next year. Because you have to go through that subadult stage first. So we can put a 0 there. No probability of transitioning from juvenile to adult. What about the probability of transitioning from an adult to a subadult? That we don't really have to look at this, but you can see that there's no flow from adult back to subadult. This is a one-direction flow. Subadults can become adults, but adults cannot become subadults, and so we can fill that in as well. So that is 0. All right. Now we have to start thinking about this top row, and the top row of a matrix is often called the fecundity because it represents not survival so much as it represents reproduction. These are survivals, right? This transition of a juvenile this year to a subadult next year, that's a survival. The transition from a subadult this year to a subadult next year, that's a survival, as is transitioning from subadult to adult stage. But this top row is special. This top row represents the chance of transitioning from being a juvenile this year to being a juvenile next year. Now that's a little bit of that's a tricky one because that could represent a survival, like juveniles remaining juvenile. But in this class, because of that confusion, I'm not going to give you any examples like that. At least I'll try to avoid that. So this top row can be representing fecundity. So it's more obvious when we look at the adult. For an adult to transition and become a juvenile next year, what you're really saying is the adult survived and it gave birth, and those new individuals in the population are now juveniles. So there's a transition from adults producing juveniles, subadults producing juveniles, and juveniles producing juveniles. So these are all reproductive events, and that's why this whole top row is basically called the fecundity row. Now let's look at the InsightMaker model again and refresh our memory on fecundity and how, which life stages contribute new offspring into the population. Well, in this case, it's only the adult stage that contributes offspring. So adults are producing offspring at this per capita birth rate. Subadults and juveniles do not produce any offspring. All right. So because we're representing this row as fecundities, we can say juveniles are producing 0 offspring in the next year. Subadults this year produce 0 offspring in the population the following year, but adults do produce, and that rate is per capita birth rate of 4. All right, so approximately 4 offspring per female, or 4 females per female. So let's get back into the whiteboard and just finish that up. So now we have a full matrix. Our transition matrix is fully fleshed out, and we can go ahead and move this into R. All right. So now that we have an idea of how we can translate this model into a matrix representation, let's go into R and implement a matrix population model together. All right. So if we go into R Studio, remember we're in lecture 7.R. This is a script you can load up from the website, and we will go to where it says in-class demo, convert an InsightMaker model to a matrix population model. So what we're going to do first is we're going to create a blank matrix in R. So one way to create a matrix in R is just to use this matrix function, and we say we want 3 rows and 3 columns because we have 3 stages that we want to represent. And so we're going to make a blank matrix, and let's name the stages. So these 3 stages are juveniles, subadults, and adults. And we're going to name the rows of the matrix, and the column names of the matrix are going to be these stage names, these life history stages. So when we have this matrix up now, we have a matrix of all zeros because we haven't filled it in yet, but we have the 3 columns correctly labeled according to the life history stages and the 3 rows. So a transition matrix is always a so-called square matrix because it has the same number of rows as it has columns, and each row and each column represents a life history stage. So each of these elements represents the transition from individuals in this stage, in the column stage this year, to the row stage next year. All right. So we can start filling in the matrix. So we know, for example, that the first row, first column is going to be 0. So even though it already is 0 here, but we could force it to be 0 again by using this bracket notation, saying take this matrix, take the first row, the first column, and we'll call it equal to 0. Now if we go back here, we remember that the second row, first column should be 0.3. So let's look at that and say the second row, first column should be equal to 0.3. And so if we run these lines, we now see that we have correctly filled in the second row, first column as 0.3. And we can keep filling it in. In fact, there's a faster way to do it. We can fill in entire columns at a time. So we can fill in this whole first column as 0.30, just like here, 0.30, and the second column as 0.4.1, and the third is 40.85. And let's just make sure that those numbers are correct. So we have 0.30, 0.4.1, 40, and 0.85. So let's run those lines, and then we can see we have a fully worked out transition matrix that we translated from our InsightMaker model, and now we're ready to do some matrix population modeling in R. We have the transition matrix. All we need is the initial abundance vector, because in order to compute the abundance next year, we need to know the abundance this year, and we need the transition matrix. So to start the population off, here's our initial abundance vector. We have 40 juveniles, 0 subadults, and 0 adults. And let's just make sure that that's how our InsightMaker model is also parameterized. We should start off with 40 juveniles, 0 subadults, and 0 adults. So what we're going to try to do is replicate exactly this model, but we're going to do it in R using matrix population modeling, just to show you that these are equivalent representations of this population. All right, so I'll get out of this and go back into R, and we can make this initial abundance vector. I will name each of the elements according to the stage, so that this is starting off with 40 juveniles, 0 subadults, 0 adults. And let's run a simulation for 40 years. And in order to compare these two, let's make sure this is also running for 40 years. And it is 40 years. So that's good. Again, we want these two to be totally comparable. Now let's go back into R. And first we're going to create this is basically making a storage matrix or storage array. I try to avoid using the term matrix in multiple ways. Make a storage array to store the abundance in each stage in each year of the simulation. So that's what we're going to do. Just make it a comment so that I know that's what I'm doing. And once we run this, we'll name the rows and columns, and we'll set the first year equal to that initial abundance vector that we already set. So this storage vector is going to look something like this, or storage array, I should say. It's going to look something like this. The first year, you have 40 juveniles, 0 subadults, 0 adults, and then we're going to fill in all these remaining years from 1 all the way to 40 using matrix multiplication to compute the abundance in each year. So we're going to use a for loop, going to loop through all the years all the way from year 1 all the way to the final year, year 40, and we are going to use matrix multiplication. So we're going to we'll start off in this column of the storage array. So the second column basically represents year 1. So we're starting off at year 1, right? The second column, we're going to loop through the second column all the way to the n years plus 1 column, or the 41st column, which represents year 40. And when we start off, we're going to be in this year 1, and we're going to compute the total abundance of juveniles, subadults, and adults using matrix multiplication. We're going to take the previous year abundance vector and multiply it, this matrix multiplication, multiply it by the transition matrix we just put together up here, right? So TMAT, remember, looks like this. And let's run it. Let's see how it works. Let's just run that for loop. And when we do, we see that we now have an actual number of individuals each year, and it is looking like it is growing exponentially, slowly but exponentially. And by the end of the simulation, we have about 18 juveniles, 8.5 subadults, and 4 adults. Let's look at the results as a plot. So we're going to use the plot function in R, and we'll first make a blank plot. Sorry. Make a blank plot there, and we'll specify that we want each life history stage to be colored differently. So I'm just using this rainbow function to grab 3 colors. Each of those represents a different color from the rainbow. And we're going to plot each of the life history stages. The juveniles, so this S is going to represent first juveniles, then subadults, and then adults, 1, 2, and 3. And for each time, we're going to plot out the trajectory of abundances in the juvenile stage, and then we'll do the trajectory of abundances in the subadult stage, and then the adult stage. And each time, we're going to use a different color, and we're going to connect them with lines. This type equals L just means we'll connect them with lines, and the line width, we're just going to make it a little bit wider than a normal line so we can see it better. And there we go. That's our trajectory over the next 40 years. All right, I'm going to add a x-axis label using this axis statement, and then I'll add a legend to represent juveniles, subadults, and adults, and I can zoom in and see this a little better. Probably best if I just make this a little bigger here and then rerun this. It should look a little better, you'll see. And now we see that it looks pretty similar to what we just observed in InsightMaker. Let's take a look. So it looks like the population of juveniles is ending up at around 20. Let's see if that matches. So if we simulate this and look at the number of juveniles, we have about 20 juveniles. Let's, if we wanted to make a table, we could even check to see if the numbers are matching. So let's add a display. We'll add a table that's, let's say, juveniles over time. And the data are going to be the total juveniles. All right. And I will apply. So now we see that we start off with 40 juveniles, we get to a very low number, and then it starts to go up after it gets into stable age distribution, and we end up with 17.97. Let's see if that matches what we see in R. So if we look at this all years, and specifically we want to look at juveniles, 17.973, juveniles after 40 years, 17.973. So we did, in fact, perfectly replicate this InsightMaker model, but we replicated it using matrix population modeling in R. So pretty cool. We basically, when we built age-structured populations in InsightMaker, we did build a matrix population model without even knowing it. All right. Now, before we end the video, I just wanted to go over some of the limitations of matrix population models. Matrix population models are great. We have already shown that they can help simplify complex population representations to project population abundances many years into the future in a really simple and straightforward way. And we can use tricks of matrix algebra to compute important population parameters such as lambda and stable age distribution. But there are some limitations to matrix population models. Now, most importantly, what about density dependence? In this past couple lectures, we've introduced a new level of realism in our model, that is age structure, but we've been ignoring another type of realism that we introduced earlier, and that is density-dependent population regulation. So what happened to density dependence? Well, part of the issue is just that it gets much more complicated when you have age-structured populations to start thinking about density dependence, because previously we had a vital rate. Maybe we'll just consider the simplest density-dependent model where we had the intrinsic rate of growth, R, and that was fixed across all individuals in the population regardless of age. Now we have multiple vital rates. We have the transition rates from juvenile to subadult and from subadult to adult, and we have the different birth rates associated with subadults maybe and adults, and we have the potential of subadults remaining subadult, surviving and remaining subadult. There's so many different vital rates, and we have to decide which of those vital rates is density dependent, right? Every one of those vital rates could change as density goes up. Do all of them change? Do some of them change? It depends, and that is the problem. There's too much possibilities. It gets very complicated, but that's, we're applied ecologists, and we always have to deal with complex systems. So that shouldn't stop us, but it's why we kind of stop thinking about density dependence for a little bit as we start wrapping our minds around age-structured populations and matrix populations, because it would be too much to try to introduce density dependence and age structure at the same time. So how do you incorporate density dependence in a matrix population model? And you never mind, how do we start incorporating things like prey-predator dynamics into matrix population model? And that's where I say cue brain explosion, because, and we're not going to have to get there really any time in this course, but we will start talking about prey-predator interactions later in the class, and competition interactions, but that is between species or among species. So there are ways to incorporate density dependence and even things like competition and prey-predator dynamics into what is otherwise a matrix population model, but of course it is more complicated. I would also say that whatever you can do with a matrix population model, you can also do in InsightMaker. You don't need matrix population models. They're there to make your life easier, but if we want to do projection, we can, if we want to find stable age distribution even, you want to find lambda. I mean, you could basically figure these things out just building your models in InsightMaker, and InsightMaker makes it relatively straightforward to make any particular vital rate density dependent if you want to. We've already shown how you can make per capita birth rate and per capita death rate both functions of density. Now you could do that with any of the parameters in a stage structured population model like this subadult mortality rate or adult mortality rate could be made to be dependent on density. Like we could use this total population as a proxy for density and make this a function of total population. So the mortality rate increases as the total population goes up or something like that, right? So we could do that. And we already know how to do that. There we are. I guess I would just end by saying that matrix multiplication makes our life easier, but we shouldn't think of it as the be-all and end-all. Knowing how to do computer programming in tools like R and InsightMaker really is more powerful and flexible than just relying wholly on matrix population model approach. Now, in previous iterations of this class, I've done a whiteboard review of matrix multiplication, but I'm going to hold off on that until the intro to Lab 4. So I'll post a video as part of Lab 4 that goes over matrix multiplication. So I'll leave that out of this video. So I'll end the video just by describing the top hat activity that we will be doing in class this week and that you're asked to answer in our top hat lecture page. And that involves not translating an InsightMaker model into a matrix, but translating a verbal description of a population into a matrix. And you should know that this is also part of Lab 4. So you'll have a chance to talk about this question in groups this week and give an initial guess at some of these parameters, and then you're asked to repeat this as part of Lab 4. Here's the description. We assumed that the red-tailed hawk life history could be described in terms of 3 major life stages: hatchling, that is the first year of life; juvenile, which are largely individuals in their 2nd year of life; and adult, generally the 3rd year of life and beyond. Adults are the primary reproductive stage and produce an average of 3 new hatchlings each year. Juveniles are expected to produce only 1 new hatchling each year. We assume that adults experience an average of 18% mortality each year. Juvenile mortality was set at 30% per year. Approximately 5% of juveniles remain in the juvenile phase each year, and all other survivors transition to the adult stage. Finally, hatchlings had a 20% chance of surviving and transitioning to become juveniles. We initialized the population with 1,000 hatchlings, 150 juveniles, and 5 adults. So this is written like a method section in a peer-reviewed paper, and you're asked to take this information and try to make a transition matrix. We have 3 life stages, so it's going to be a 3 by 3 transition matrix, just like we did earlier here. And try to take the information in this paragraph and translate it into a transition matrix. Now, in this in Lab 4, you will be graded for correctness, but in this exercise in Top Hat, this is not graded for correctness. This is just participation. So just do your best, and I will see you in class.